All right, hello guys. This is Mr. Hebner. We are doing the Charles Law Lab, and we got some great students with us here helping us out. There we go.
Get in the shop, Michael.
There. There's Michael. So what we got, Charles Law, we're looking at volume and temperature, and as we increase temperature, we should be seeing the volume increase as well. And we got a nice lab setup right here. We're going to take room temperature first. What we did was we took a utility clamp and put it on a ring stand to hold our syringe. And notice how it's at 30. We had to unplug the stopper and pull it out and stop it up again. All right, and it's at 30. We're going to put this back in here. And let's see, maybe, there we go. And Jake, if you want to fill that up with water, so you're either going to have to pour, okay, you might have done clamp it here. There we go. And I would fill it up 3/4 full of water. And what we're going to do is we're going to let this sit in there for 5 minutes. We're going to pull it out. We're going to push this down because it could get stuck. We want to make sure it's not stuck. And yeah, just as Wilson was saying, we got to use the thermometer to check the temperature at the end. So it should be around 20 degrees Celsius, which is like room temperature. We're then going to heat it up to 4 different temperatures. The first one, I think it says, is what?
50.
50. We're going to heat it up to 50 degrees Celsius. That could be 52, could be 48. Doesn't matter, just as long as it's different than 25 and it's warmer. And we're going to heat it for 5 minutes there. We're going to pull the stopper out, push it, record the volume and the temperature at that time. And we're going to repeat that a total of 4 times, so we got 4 data points. And that's pretty much it. The rest of the lab is just sitting and waiting for the temperature to rise. All right. We're going to put it on pause because we don't need you to sit there that whole time. All right. All right, guys. What we got for our temperature was, it was actually 18 degrees Kelvin. And our volume we started was at 30 centimeters cubed. So that's our initial temperature. We've got volume divided by temperature, so I'm going to do 30 divided by 18 here. Calculate that out. 30 divided by 18. That's 1.66. All right. All right, we're going to get 3 more data points. So I'll put this on pause till our data is ready.
We're ready to scientifically remove this stuff. You know what I'm saying?
All right. Yeah, so my assistant here, Wilson, he's going to... he's going to push down the syringe.
Oh my God.
There we go. Look at that. Because we want to make sure it's not stuck.
Damn!
Oh, that's good.
Okay.
And then he's going to record the volume. So what volume do we have there?
30. Wait, what? Look at the water?
No.
What?
In there, the gas. There.
30. Is it not?
Yeah.
What line is it?
A little bit above the 31.
31 and a half.
Oh, it's 30 and a half?
Yeah, I know. No, we're going to round up just to make it look prettier.
Yeah, well, it's like 3/4.
All right.
Maybe
31.
We'll say 31. Yeah.
31.
We'll go with 31. And what's the temperature on the thermometer?
60? It's like 60, 59.
60, 59. So what are we going to go with? 60? Okay.
Yeah.
All right, we'll go with 60. All right. And then what we're going to do is we're going to put it back down and then heat it again all the way up to 80. That's our goal.
80.
All right.
Oh, I'll take it a minute.
Oh, we're pumping.
All right, so just recording our temperature. We had 59 degrees Celsius. And our volume was, what was it? 31. All right. Okay, and I just noticed it's in Kelvin here. So remember, gas laws have to be in Kelvin. You cannot stay in Celsius because we're dealing with kinetic molecular theory. And that's based off of movement of molecules, which Kelvin looks at. Celsius just looks at freezing point of water, boiling point of water. So I got to add 273. Okay, 18 plus 273. That's 291. And then 59 plus 273. That's 332. All right, and then this is going to be 30 divided by 291. 30 divided by 291, 0.103. 0.103. And now here we're going to have 31 divided by 332. 31 divided by 332, 0.093. All right, and we're going to get 2 more data sets. All right, we got another assistant right here. Oh yeah, this is gonna be the 3rd data point. It's at, what's the temperature? 80 on the dot. Nice. I'm gonna lift this up. Make sure you push the syringe down. Just make sure it's not a false reading. Oh yeah, that's good. All right. And we're gonna record the volume. Oh, look at that.
Yo!
Whoa.
Sorry.
That's crazy.
33.
33. All right.
At 34 for 50.
No, yours was at 31.
No, ours was at 34 for 50.
Oh.
We don't care about ours. Ours is
You didn't even turn your hot pad on.
We're doing this one.
All right. So we're gonna submerge it again and raise
Crank
it all
the
the
heat up
way.
to 10. We're gonna burn that one out.
All right, to 95 at least. All right. All right, guys. We're 80 degrees Celsius on the dot, and it was it 34 or 33?
What was the number? I think it was 34.
34. All right, it was 34. Good thing we got one person that remembered. All right. All right, then we're going to add 273 because we want to convert it from Celsius to Kelvin. Plus 80. 353. And we're going to take 34 divided by 353. And I'm getting 0.096. 0.096. All right, and we just got one more data point. All right, what we got going on is our last data point. We got another assistant right here. It's at, what's the temperature?
Wow, you're so unprofessional. Just do the.
All right, what am I doing?
Check the temperature.
Oh, check the temperature. All right, we're at like 95.
95. All right, and then press the syringe down. And there we go.
Oh, wow.
And what's the volume at?
Oh, whoa, we're at like 35.
Oh, wow.
Nice. 35 on the button
That's
at 95 degrees Celsius. All right. All right, the last data point. 95 degrees Celsius. And it was 35 for our volume. We got to add 273 to convert it to Kelvin. 95 plus 273, 368. All right. We're going to do 35 divided by 368. We're getting 0.095. All right. And what we got going right here is our value is going down overall. It should be going down. We got an anomaly right here, which means this data point wasn't the most accurate. There's some things that could have gone wrong. But if your trend is overall going down, that is a good result because it's showing a direct relationship. As temperature goes up, so does volume. All right, that is Charles' law. All right, what we're going to be doing now is graphing this, and it's way easier, especially on the directions that are on this particular lab, to do it on a digital platform like Desmos. All right, so here is our data set. think we just typed it in. So our data is 291 Kelvin. And then we've got 332. And then we've got 353. And then we got 368. Okay, so what I did actually is I did add item tables because we want to put a table in here. So we're going to put the 291 in there, and then 332, enter, 353, enter, and 368. See, it was giving us suggestions for a linear line. And this is our data point. It's not so good. All right, and then Y is 30, 31, 34, and 35. All right, this I'm going to get rid of. And we want to graph this. All right, I'm trying to figure out where to find this, so I zoomed out because I'm at 291 here. So I continue to zoom out, and I can find it right here. And as you can see, the temperature goes up as my volume goes up overall. So we're going to try to create an equation for this. Okay, so we want to do a line of best fit. So this is unique to Desmos. We're going to do Y1 and then that weird symbol. It's in the top left button of your keyboard right below the escape. I did shift that button, and it's MX1 plus B. And there it is. It just plots our best fit line. It did it. And where it's at 0, that's where are we talking about? So actually, temperature is 291. Yep, on Desmos. So right here, this is absolute 0. It's 10.06. So on our plot, it says realizing that negative 273 degrees Celsius is the actual value of absolute 0. Calculate 3% air. Oh, now write the number in degrees. Yeah, so it says show your work to find the x-intercept, the temperature at which volume is 0. So this is where the temperature is 0 Kelvin, and it's 10.06. Centimeters cubed. Alright, let's switch to this. Technically, absolute 0 is theoretical. We can't get to it. And the volume should be 0 centimeters cubed at absolute 0. Which again is impossible. That's why absolute 0 is impossible, and then getting to 0 centimeters cubed is impossible. But according to our data, it said it was 10.06 centimeter cubed at absolute 0, which means we're a little bit off. It makes sense because it was a very rudimentary lab, and there's a lot of ways we could have made mistakes, such as trying to get the exact temperature. Super hard because when you're heating it, it's going to go past, and you turn it off, it's going to get colder. So that's super difficult. Very basic lab, but the main idea is temperature, as it increases, so does volume. That's the main idea. All right, that has been the Charles Law Lab.